Welcome back to this video. Coming to the factors that are affecting the chemical shift. In the previous video, we had taken up the electronegativity, uh, which affects the chemical shift values to a very greater extent. So in this particular discussion, I would like to take up the hybridization effect. I would like to simply flash the slides of electronegativity before I proceed. So coming to the effect of hybridization. So here we are going to study how the hybridization is actually affecting the chemical shift values and how is their appearance with respect to the hybridization. So coming to the sp3 hydrogens. Hydrogens that are attached to sp3 hybridized carbon atoms usually resonate between these 0 to 2 ppm. Okay, so the carbon which is sp3 hybridized and the hydrogens attached to this particular sp3 hybridized carbon atoms, they usually resonate between 0 to 2 ppm. The methylene group or the CH2 hydrogens, in particularly this particular hydrogen, these particular hydrogens usually appear at the greater chemical shift values, that is near to 1.2 to 1.4 ppm, than do the methyl group hydrogens. Okay, so compared to the methyl hydrogens, these methylene hydrogens, they appear at the greater chemical shift values, that is around 1.2 to 1.4 ppm, than compared to the methyl hydrogens. The methane or tertiary methane hydrogens, they usually occur at higher chemical shift than secondary hydrogens, which in turn have a greater chemical shift than do primary or methyl hydrogens. Compared to the previous primary and secondary hydrogens or hydrogens that are attached to primary or secondary carbon atom, the tertiary the protons that are attached to tertiary carbon, they are the methane hydrogens. The appearance of the delta value happens to be at a greater delta value when compared to the previous two. So this is the chart where the primary or the protons that are attached to primary carbon or the secondary or the tertiary carbon, you can see their appearance in the 0 to 10 delta scale, 0 to 15 delta scale. So this is the general understanding of this sp3 hydrogens. Coming to the sp2 hydrogens, the simple vinyl hydrogens are the hydrogens that are attached to the carbon, which are double bonded carbon atoms. So they have resonance in the range of 4.5 to 7 ppm, and in a sp2 1s CH bond, the carbon atom is having more S character, which is usually 33%, which effectively renders it has to be a more electronegative than compared to the sp3 carbon, which is having the S character of 25%. So there is a lot of S character of this sp2 hybridized carbon compared to the sp3. So it behaves more electronegative, or the sp2 carbon atoms, they behave, or this sp2 1s CH bonds, they behave to be a more electronegative since they have more S character. And in the previous video we have seen that the more electronegative the character is, or the more electronegative the substituent is, the delta values are shifted towards the higher values or towards the deshielded region of the NMR spectra. So since the atom or the carbon atom has more S character, it acts to be more electronegative when compared to the sp3 carbon. So that's why the sp2 carbons, they behave as more electronegative when compared to the sp3 carbon atoms. The s orbitals hold electrons closer to the nucleus than do the carbon p orbitals. The sp2 carbon atoms holds its electrons more tightly. This results in less shielding of the H nucleus than in an sp3 1s bond. Thus, vinyl hydrogens have a greater chemical shift, that is 5 to 6 ppm, than aliphatic hydrogens on sp3 carbons which have usually 1 to 4 delta values. So the sp2 carbon atoms, they behave as or these sp2 carbon atoms, they hold the electrons more tightly, and this results in slightly deshielding of the H nucleus in an sp3, uh, results in a less shielding of this hydrogen nucleus than in the sp3 1s bond. Thus usually the vinyl hydrogens have the greater chemical shifts, and they appear to be at a deshielded region when compared to the aliphatic protons, which are on sp3 carbon atoms. So compared to aliphatic hydrogens, the vinyl hydrogen appears at the higher delta values. Coming to this vinylic hydrogens, hydrogens attached to carbon-carbon double bond appear or resonate between 4.5 to 7 ppm. The sp2 hybridized carbon atoms of the double bond has increased the S character and is therefore more electronegative than sp3 hybridized carbon atom. So usually it is the vinylic hydrogens which resonate between 4.5 to 7 ppm, and this sp2 hybridized carbon atom of the double bond or the double bond will increase the S character. So we know that increase in the S character leads to the increase in the electronegativity when compared to the sp3 hybridized carbon atom. Compared to this, as compared to vinylic hydrogen, the aromatic hydrogens usually resonate between 7 to 8 ppm, and usually, as we think, the vinylic hydrogens are also present in the aromatic hydrogens or in the aromatic rings. They do not resonate between 4.5 to 7 ppm. Rather, they appear to be at bit more higher delta values, and this is because of something what we call as magnetic anisotropy, which we'll take up in the next video. And also the aldehyde hydrogens, they resonate between 9 to 10 ppm, and these aldehyde hydrogens, they further appear in the downfield region due to the additional effect of electron withdrawing oxygen, which is a nearby electronegative atom, which deshields the hydrogens a bit more, as we have the electronegative atom and also the double bond existing simultaneously. The aldehyde protons, they further appear in the downfield region, that is 9 to 10 delta delta values. So coming to the sp hydrogens, sp hydrogens are the hydrogens which are attached to a carbon which is further having a triple bonds. The acetylenic hydrogens, that is CH-sp1s, appear anomalously at 2 to 3 ppm owing to anisotropy. Okay, so anisotropy is the next topic which I would be taking in the next video. So because of magnetic anisotropy, these acetylenic hydrogens, they tend to be quite shielded, so that's why they appear at the lower delta values. So as theoretically thinking, the acetylenic hydrogens should appear at the higher delta values, but they do not appear at higher delta values, rather they appear at lower delta values, which is because of this magnetic anisotropy. That the case is similar with the aromatic hydrogens and aldehyde hydrogens. An sp carbon should behave as if it was more electronegative than compared to sp2 carbon. This is opposite of what is actually observed. This is because of the magnetic anisotropy, which I will be discussing in the next video. So here we conclude with the hybridization, which affects the chemical shift values.